This is the second part of 7.1, talking about the structure of the atom. And now we're going to talk a little bit more specifically about the structure of the nucleus. Before we do that, though, let's touch on a few things just to make sure we are all on the same page. The structure of an atom overall has two basic parts. It has a nucleus, which is the source of most of the mass of the atom, and then around it it has the electron cloud, which is where the much smaller electrons exist. The overall charge of the nucleus is positive, and then obviously the electrons outside are negative. So we have electrons are in the electron cloud that's outside the nucleus. The protons, which are positively charged particles, are in the nucleus itself. And along with the protons, we have a third particle, which we know about thanks to James Chadwick, which is called the neutron. And neutrons, as may be guessed from their name, are neutrally charged. They are also in the nucleus. And so, charge, electrons are negative, protons are positive, and neutrons have zero charge. And if we compare them based on size, if we go by relative mass, or what we call atomic mass units actually, the electrons actually have a mass of 0, and the protons and neutrons each have a mass of 1. Now, obviously the electrons don't have an actual mass of 0, but it's about 2,000 times smaller than the mass of a proton or a neutron. And so when we're really talking just in general terms about the mass of an atom, the electron's mass is inconsequential. And we're going to call the proton and neutron masses 1, even though they have slightly different masses as well, which we'll talk about a little bit later on. Now, despite the significantly larger size of the proton, as I said, the proton is roughly 2,000 times the electron size, the electron mass. The magnitudes of their charges are identical. So as strongly negative as an electron is, a proton is the same level of, has the same level of what's called positivity. So a proton and an electron in terms of charges will completely cancel each other out. They have identical magnitudes, just opposite signs, positive and negative. So now let's look a little bit more at this part right here, this nucleus. The nucleus, as we know, is made up of both protons and neutrons. Collectively, these are called nucleons. When we write out chemical formulas and we're talking about the nucleus, and we're talking about nuclear structure, we're going to see it written in this generic form here. In this form, X represents the chemical symbol. So whatever the symbol for that element is, that's going to be written there. This superscript here, let's change the color. This A, this represents the mass number. Okay, the mass number, or sometimes the atomic mass, it's called, and this is in AMUs. Then the third letter that we have here, Z, Z is the atomic number. Now, the atomic number is equivalent to the number of protons, or it tells us the number of protons. So that's really, that gives us everything we need to know. The one piece of information that's not specifically stated here is the number of neutrons in the nucleus. But given what we have, we can calculate the number of neutrons. Now, if we recall from a short time ago, the mass of a proton is 1 AMU. The mass of a neutron is also, or the relative mass of a neutron is also 1 AMU. Electrons, we're not going to worry about at this point. They're so small the mass doesn't matter at this moment. So, if we're looking at the mass of an atom, of a nucleus, the total mass of the nucleus is going to be the mass of the protons plus the mass of the neutrons. So, this mass number up here is the protons plus the neutrons. So, mass number equals, and we'll just symbolize P and N, protons plus neutrons. If we want to find the number of neutrons, it's a simple subtraction. Mass number, we'll just say M, little pound sign, mass number, minus the number of protons. That gives us the number of neutrons in a particular nucleus. So we can symbolize, let's write this all in symbols. A equals P plus N. Z equals P. And when we're talking about normal atoms, not ions, not anything charged, in an atom, atoms are neutrally charged. And so if something's neutrally charged, that means there's zero net charge. So that means the pluses and the minuses cancel out. And so the number of protons is equal to the number of electrons. So with these three pieces of information, we can pretty much figure out anything we need to about the particular nucleus. And this atomic number, this is Z right here, this is unique for every element. We've seen the periodic tables before. We know that it's ranged by the number of protons, starting with hydrogen at 1 going on up. That atomic number, that's what we see, that's that big number on the periodic table, that's unique for every element on the periodic table. The number of protons is what makes an element unique. It's what gives it its unique chemical characteristics, its chemical properties. The number of protons is what defines an element. It's what makes that element unique. Other things about an element can change. The number of neutrons, as we'll see, the number of electrons, but the number of protons, if the number of protons were changed, it would be a totally different element. So let's look at a specific example. Let's take lithium as an example. The atomic, or the chemical symbol for lithium is Li. Lithium is atomic number 3. Now if we look at the periodic table, we'll see that the average atomic mass for lithium is 7. So if we were to write it out in this particular format, here's our element symbol, here's the atomic number, the number of protons, and here's the atomic mass, 7. How many neutrons then does lithium have? Well, the atomic mass is 7. Of that 7, we have 3 protons, so there must be 4 neutrons. Another example would be, we can use beryllium. Beryllium is atomic number 4, and if we look at the periodic table, we see it has an average atomic mass of 9. How many neutrons does beryllium have? Total mass of 9 minus our 4 protons gives us 5 neutrons. So pretty straightforward. Not all atoms of an element have to have the same number of neutrons, though. As I just mentioned, the specific element is defined by the number of protons, but what we'll find is that not necessarily do they all have the same number of neutrons. And when we have an element that has the same number of protons but a different number of neutrons, it's what we call an isotope. And isotopes have a number of uses, but essentially you have a nucleus let's say we have something like hydrogen. Hydrogen is the simplest element. In its most basic form, the nucleus of hydrogen has a single proton. If we had a nucleus of hydrogen that has a single proton, we would write it and it would look something like this. One proton, the atomic mass is 1. Straightforward. But hydrogen can occur in multiple forms. You can also have a nucleus of hydrogen that has 1 proton and 1 neutron. So here, we still have the same element, it's still hydrogen. We still have 1 proton, but now the atomic mass is 2. This is called deuterium. There's also a third isotope of hydrogen. And in this particular isotope, you still have 1 proton, because the proton determines the element, but we have 2 neutrons. And so in this case, again, atomic number is still 1, but the mass number here is 3. And this is what we call tritium. And so there are 3 distinct versions of hydrogen. They all have one thing in common. They have the same number of protons, 1. But they all have a different number of neutrons. Now really the only thing this changes is the mass of the element. So hydrogen, H1, has a mass of 1. Tritium has a mass 3 times the size. It's 3 times as massive. And you can actually see this if you were to fill 3 balloons up, one with hydrogen, one with deuterium, and one with tritium, and you were to let them all go. The hydrogen balloon would be the least dense. It would float the fastest up. The deuterium one next, and then the one that would rise slowest would be the one that was filled with tritium. So they're going to have different physical properties, but their chemical properties are still going to be the same. They're going to react in the same fashion because they have the same number of protons. Now, a quick review of the forces that we're dealing with when we talk about the nucleus. We mentioned before that the force between the electrons and the protons is what we call Coulomb force. It's an electrostatic force as a result of the opposite charges of the protons and the electrons. But inside the nucleus, where you have all of those protons, all of those like charges, there's actually an electrostatic Coulomb force there too. But there's repulsive. All of those like charges, just like if you take 2 of the same side of a magnet, 2 norths, and you bring them together, they repel each other. They push each other away. The same thing's happening in the nucleus to all of those protons. They're all pushing each other away, trying to get away from each other. So something has to be holding them together. And in the nucleus, it's the neutrons, and they're exerting what we call the strong nuclear force. It's a very short distance force. Once you get too far away, it gets weak very quickly. But within a short distance, it's an extremely strong force. It's much stronger than the electrostatic force, which is why the nucleus holds together. But what you'll see if you start looking at the periodic table, when you look at the smaller elements, you'll see that the number of neutrons is roughly the same as the number of protons. But as you get to the larger elements, you'll see that there's many more neutrons than protons. And the reason for that is twofold. One, there are more protons, and so there's more of that repulsive electrostatic force pushing away. But additionally, at some point, the size of the nucleus actually gets larger than the distance over which that strong nuclear force can exert itself. And so you have to have more neutrons in order to hold that nucleus together. As we get to larger and larger nuclei, they become what we call unstable because there's just not enough force to hold that nucleus together for too long. And eventually they decay, and which is what happens when they fall apart.